Yes, thanks so much for the introduction. Hello, everyone. My name is Haebom Lee, and I'm delighted to be here today to talk about the role of generative models in data-centric AI. Before we dive into the topic, let me briefly introduce myself. I'm currently leading the DAS R&D team as a principal research engineer at AIMMO. And we are working on some exciting projects, and I'm eager to share some of our work with you today. Prior to joining AIMMO, I was a doctoral student researcher at Bosch, where I gained valuable experience in the field. I've also had the opportunity to work as a student researcher at various institutions, including KIST Europe, the German Research Center for Artificial Intelligence, and MMCI at Max Planck Institute. On the academic front, I'm currently pursuing my PhD at Heidelberg University under the supervision of Professor Carsten Rother, and I look forward to graduating this year. Wish me good luck. And I hold a master's and bachelor's degree in computer science from KAIST. My primary fields of interest include outdoor lighting estimation, simulation, synthetic data generation, and computer vision. These areas form the backbone of my work at AIMMO and will be the focus of our discussion today. Yes, we will begin by discussing the background and importance of data in AI, and we will explore the role of generative models in data-centric AI and how they can be used to create synthetic data that can improve the performance of AI models. Afterwards, we will discuss the need for synthetic data in autonomous driving and how we can help in developing more robust and reliable AI systems. Following that, we will look at how synthetic data can be generated for different operational design domains and the benefits of this approach. We will also cover the concept of data curation in the latent space and how we can help in improving the quality of the data set. Then, we will delve into the concept of closed-loop learning and how it can be used to continuously improve the performance of AI models. Towards the end, we will discuss the challenges and limitations of using generative models for synthetic data generation. Let's begin by understanding the importance of data in AI, and more specifically, in autonomous driving. Data is often referred to as a fuel for AI systems. A car needs fuel to run, and similarly, AI systems need data to operate and learn. The more high-quality data we have, the better our AI systems can perform. In the context of autonomous driving, the need for data becomes even more critical. Autonomous vehicles require a huge amount of data for various tasks, such as path planning, interaction with the sensory system, and perceiving the surrounding environment. This data is what allows these vehicles to navigate safely and efficiently on our roads. However, it's not just about the quantity of data. The quality of data is equally, if not more, important. Poor quality data can lead to poor decisions, while high quality data can lead to accurate and reliable outcomes. Traditionally, the focus in AI research has often been on refining and enhancing the structure of neural networks to boost performance. However, there's a shift happening towards a more data-centric approach. Data-centric AI is an approach that emphasizes improving data quality, not just model architecture. This is particularly relevant in autonomous driving, where high-quality data is essential for training reliable and safe driving systems. But the benefits of data-centric AI don't stop there. Not only can it reduce training time and the storage needed for data, but it also enables us to develop consistent methods for collecting and labeling images and facilitates the optimization and updating of models. So instead of just building a better engine, we are ensuring that we have the best quality fuel for our AI models. As we delve deeper into the world of autonomous driving, we quickly realize that it's a field that requires a multitude of AI systems, each demanding vast amounts of data for effective operation. This is where the concept of data-centric AI comes into play. Data-centric AI allows us to use our data more efficiently, as we discussed earlier. It also helps in reducing errors and improving the performance of AI models, which is crucial for the safety and the reliability of autonomous driving systems. One of the key challenges in this field is achieving high-quality data sets and covering edge cases. This is where the use of generative models becomes highly relevant, seeing that they offer a practical solution to these challenges. And as we move forward, we'll see how influential they are in synthetic data generation. Let's now turn our attention to generative models, a type of AI that can generate new data instances. These models can interpret and manipulate pre-existing data, creating new instances that can be used for training AI systems. One of the most well-known examples of generative models is generative adversarial networks, or GANs. And the GANs consist of two networks, a generator and a discriminator. The generator's job is to create new data instances, while the discriminator evaluates them for authenticity. These two networks compete against each other, and in doing so, they improve the quality of the generated data. Furthermore, another example of a generative model is the diffusion model. A popular type of diffusion model is the stable diffusion, which can generate data based on a given input. For instance, as you can see here, it can generate an image from a text prompt. This provides a powerful tool for synthetic data generation, as it allows us to create specific types of data on demand. In terms of autonomous driving, these generative models can be used to create a wide variety of synthetic data, which can greatly enhance the performance and robustness of AI systems. In the realm of data-centric AI, generative models play a pivotal role. They are capable of capturing complex data distributions and generating synthetic samples, which are invaluable in enhancing the effectiveness of AI systems. The continuous evolution of these models has led to significant advancements in their capabilities, making them a powerful tool. One of the key advantages of using generative models in data-centric AI is their ability to enrich our data sets. They can generate synthetic data that improves the quantity, quality, and variety of data available for training AI models. This not only optimizes the training process, but also allows us to create specific data that might be difficult to obtain from the real world, thereby broadening the scope of scenarios our AI systems can handle. Let's now turn our attention to a fascinating study titled Augmented Reality Meets Computer Vision: Efficient Data Generation for Urban Driving Scenes. This research provides a compelling example of the impact synthetic data can have on deep learning. The authors of the paper propose an innovative approach that combines real and synthetic data to train semantic instance segmentation and object detection models. They augment real-world imagery with virtual objects of the target category, creating composite images that retain the realistic background appearance while introducing a variety of complex object arrangements. The figure on the left side illustrates the significant improvements in the performance of deep learning models when synthetic data is used in conjunction with real-world data. This underscores the potential of synthetic data to enhance the effectiveness of deep learning, particularly in complex and dynamic fields like autonomous driving. Yes, this is another paper that I would like to introduce. It's titled Fallen Person Detection for Autonomous Driving. As you might imagine, it's quite challenging to find images of people lying down on the road in typical autonomous driving data sets. This scarcity often results in bad performance when it comes to detecting individuals in such unusual positions, as demonstrated in the image on the left. The authors of this paper tackled this issue by superimposing images of people lying down onto clean road images. This strategy serves as an excellent example of how synthetic data can be used to cover edge cases, and it has led to an improvement in the performance of the detection algorithm. Let's now explore AIMMO's strategy for synthetic data generation. At AIMMO, we recognize the significant role synthetic data plays in advancing AI, especially when gathering real-world data can be both challenging and costly. Our strategy harnesses the power of generative models to create synthetic data, a key component in enhancing the performance and robustness. This synthetic data generation approach offers several distinct advantages. First, it increases the diversity of our data set, which is essential for improving the generalization of our models. Second, it substantially reduces labeling costs. With synthetic data, we can get the ground truth label for free, eliminating the need for extensive manual labeling. Last, our approach enables us to cover edge case scenarios. These scenarios, while often underrepresented in real-world data, are vital for ensuring the safety and reliability. Through this approach, AIMMO is pushing the boundaries of what's possible with synthetic data in AI, setting a new standard for data-centric AI development. Having discussed AIMMO's approach to synthetic data generation, let's now shift our focus to an important concept in the field of autonomous driving, operational design domains, or ODDs. ODDs are specific conditions under which a driving automation system is designed to function. These conditions can include environmental factors, geographical locations, and even time of day restrictions. Understanding these domains is fundamental to the safety of autonomous vehicles. Now, you might wonder why we are discussing ODDs in a talk about synthetic data. Well, the connection is quite significant. Each ODD has its unique characteristics, and to ensure the robustness and reliability of our AI systems, we need to train them with data that covers a wide range of ODDs. To ensure our AI systems are well prepared for a wide range of real-world driving scenarios, we need to train them with data that covers various ODDs. This is where AIMMO's approach to synthetic data generation comes into play. At AIMMO, we leverage synthetic data technology to diversify our data sets, simulating a variety of ODDs. This includes not just the common scenarios, but also the edge cases that are often ODD specific. For instance, we can generate synthetic data that simulates different weather conditions, seasonal effects, or even emergency situations. By doing so, we are not just enhancing the robustness of our AI models, but also reducing the need for extensive real-world data collection on the various ODDs. As you can imagine, collecting real-world data for every possible ODD can be time-consuming and costly. Through synthetic data, we are able to efficiently and effectively prepare our AI systems for the diverse challenges they may encounter on the road. Let's now take a closer look at a specific case study. And this case study illustrates the power of synthetic data generation. Consider the task of detecting road defects, such as cracks or potholes. This is a critical task not just for autonomous driving, but also for smart city applications. Traditionally, labeling these defects in real-world images involves a significant amount of manual work. Moreover, it's challenging to guarantee the consistency of the labels due to the varying nature of these defects. Now, imagine if we could create such defects on clean roads using synthetic data generation. This approach offers several advantages. First, it eliminates the need for manual annotation, as the ground truth labels are automatically generated, or you can just mark the region where you want to insert such defect, and that will be just a ground truth labeling for that. Second, it produces clean and precise ground truths, ensuring the quality of the training data. Furthermore, we can generate as much data as we want, allowing us to cover a wide range of defect types and scenarios. And last but not least, this approach significantly reduces the cost of data collection, as we no longer need to physically go out and collect images of various road defects. Let me move on to the next topic, data curation. In the realm of deep learning, we often talk about a concept called the latent space. This is an abstract, multidimensional space that encodes a meaningful internal representation of externally observed events. The latent space plays an important role in deep learning, especially in terms of data compression. It allows us to learn data features and find simpler representations of data for analysis. Deep neural networks can learn underlying patterns in complex data, which is a key aspect of data curation in the latent space. Let's now look at how AIMMO uses data curation in the latent space to improve the quality of the data set. Our goal is to identify a smaller data set that can achieve performance comparable to the model trained on the original data set, while also covering edge cases. To do this, we first project each data sample to a point in the latent space. From here, you can think of numerous ways to refine a data set in the latent space. For instance, you can find representative samples using clustering, or identify edge case samples through similarity measurement. Now let's consider how this approach to data curation fits into a broader learning process. One common method is continual learning, a process that allows a model to continuously improve as it's trained on a certain data set and retrained when additional data is collected. However, this traditional approach has its drawbacks, as the new data requires additional manual annotation work. Furthermore, this manual annotation process can lead to inconsistencies in the labels, affecting the quality of the training data. Let's explore how AIMMO applies closed-loop learning to optimize our AI models. We begin with a reduced data set to train our target algorithm. As we identify vulnerable classes or cases where the model's performance could be improved, we leverage generated models to generate the synthetic data specifically tailored to these classes. This synthetic data, which includes both the ground truth labels and input, is then integrated into our training data set. The optimization process involves combining the original data set with the newly generated synthetic data, embodying the key value of data-centric AI by focusing on enhancing data quality and efficiency. This approach not only reduces the need for manual annotation and extensive data collection, but also saves valuable time and resources. The closed-loop learning process is iterative, with each cycle aimed at continually improving the model's performance, and it makes highly effective for autonomous driving applications where conditions can vary greatly, and the model needs to adapt to diverse scenarios. Moreover, this approach also allows for the implementation of continual learning, where the model is retrained on the updated dataset and its performance is evaluated. This process is repeated for a certain number of iterations until we achieve the desired performance or we reach the given restrictions. While we've explored the potential and applications of generative models in synthetic data generation, it's equally important to recognize the challenges and limitations that come with it. One of the primary challenges is the significant computational resources and time required for training generative models. Moreover, the quality of synthetic data is intrinsically linked to the quality of real data used for training. And while synthetic data can diversify datasets by providing various scenarios, capturing the entirety of real-world complexity in synthetic dataset remains a formidable challenge. The next two things are somehow connected. There are instances where generative models may produce unrealistic data. And to prevent this, we have to come up with a way to evaluate the quality of the synthetic data. Last, the lack of interpretability and transparency in generative models can pose challenges in certain applications. In conclusion, generative models can play a significant role in data-centric AI, especially within the field of autonomous driving. The generation of synthetic data using these models can greatly reduce the need for extensive labeled data. AIMMO's approach to synthetic data generation with a focus on ODDs effectively addresses edge case scenarios. Techniques such as closed-loop learning and data curation in the latent space further enhance the effectiveness of data-centric AI. Despite certain challenges and limitations, the advantages of using generative models for synthetic data generation are substantial. Our case study provided a practical demonstration of them. As we look ahead, it's clear that progression of autonomous driving technology will continue to be influenced by advancements in data-centric AI and generative models. And I think that's the end of my talk. Thank you so much for your attention.
So could you expand on what's the strategy that AIMMO is using to validate real data against the synthetic data? What metrics are looking into? What's the strategy, or do you see any challenges there? Like, when is the synthetic data is real enough to represent the actual physical world?
So we are considering various scenarios. So the one case would be using synthetic data only for validating the model's performance. But we are also thinking of utilizing synthetic data in the training. And to validate such data set quality, we are investigating into several ways to do that. And one of the ways could be, instead of using our annotators to label the objects or semantic segmentation labels, we put them to check the authenticity of synthetic data set. So that could be a way to do that.
I see. Thanks. Go ahead.
Yeah, very great presentation. Thank you so much.
Thank you.
Are you thinking of or considering of extending your model to different sensors, LiDAR, others than camera?
Yeah, that could be also possible for stable diffusion or other generative methods, because we can also let the network to generate depth maps, for instance, or semantic segmentation maps from noise or even real-world images. So that could be a way to utilize these generative models in different ways. I strongly believe it can also generate depth map or LiDAR sensor data if you want.
Okay, thank you.
Yes.
Hi, thank you for the presentation. My question is about the generation of the video. So obviously from the auto industry perspective, we care about the spatial and temporal information, what the car is moving. So my question is that when you generate, I can see you can generate a video, the image by the GAN. My question is that do you have a process to generate the video that makes sense to the camera? Thank you.
Yes, so for as far as I know, for now it's quite difficult to generate plausible video from the noises if you use stable diffusion network. But instead, we can think of utilizing video-to-video transformation or translation, where you can put a real scene videos into the model and then let the model to convert some of its features in the video to the features you want. So like, if you want a car in a video to be a fire engine, then it's possible. But there must be some fluctuations you can observe in the video for now. But I strongly believe that this diffusion model-based generative method will be improved much better in the future.
All right, thank you.
Thank you.
Any other questions? No. Thank you so much.